So when I first heard that 1 was the same as 0.9999999 or 0.9 repeating, I thought there was no way that this is true. But now I want to show you 3 different ways to understand this craziness. So the first method kind of relies on something a bit familiar. So recall that 1/3 is just the same thing as 0.3 repeating. Or if you'll let me just write it as 0.33333. Now if we take both sides of the equation and multiply them by 3, on the left-hand side, 3 times 1/3 is just 1. And on the right-hand side, if we multiply each digit by 3, we'll get our 0.99999 or 0.9 repeating. So our second method involves a little bit of calculus. So let me give you some background information. So in calculus, there are these things called geometric series. Basically, this is just a fancy way of describing a really cool way of adding up numbers. So geometric series follow this pattern. I'll explain it in just a second. So here, we just have some number, a, but notice each time, for each subsequent term, we're multiplying it by another factor of r. And this goes on and on and on forever. But the really cool thing about this is that we can actually find out what all of this adds up to. So it adds up to a divided by 1 minus r. So how does this relate to what we're talking about? Well, 0.99999, so on and so forth, we can think about that as each digit adding up together. So 0.9 plus 0.09 plus 0.009, and before I bore you, I'll leave it there. So if we think about our 0.9 as our a value, well, 0.09 can be thought of as 0.9 times 0.1. And then 0.009 can be thought of as 0.9 times 0.1 squared. And as you maybe can guess, 0.0009 can be thought of as 0.9 times 0.1 cubed. And this pattern actually repeats. So using our rule up at the top here, we know that this is equal to a divided by 1 minus r. So again, this is our a value, and here's our r value. But now, if we simplify this, this is the same as 0.9 divided by 0.9, or 1. So again, we get 0.9 repeating is the same as 1. So before I move on, I want to quickly make one note that this relationship that we used up top here, this only works when r is in between -1 and 1. If r isn't between these two numbers, then this relationship doesn't hold true. So our third method uses a little bit of mathematical logic. All right, probably a lot of bit of mathematical logic, but let's start from the beginning. So a mathematical statement or a claim is either true or it's false, one or the other. So there's this method for proving that a statement is true called proof by contradiction. So the way that it works is that if you want to prove a statement is true, you actually assume that the negation of the statement or the opposite of the statement is true. So you're assuming the original is false. And then after that, you're showing that, oh, okay, if we assume the opposite is true, then this wild, crazy thing happens. We call this the contradiction. So if something impossible happens when you assume the opposite, then that must mean that the original has to be true. So here's just a really silly example. So consider the statement, it did not rain every day last week. So if we want to prove that this statement is true, we'll assume the opposite. So assume for a second it did rain every day last week. Well, now we want to show a contradiction. So for example, it did not rain on Tuesday. See how this contradicts with the opposite statement? So how can it rain every day last week and not rain on Tuesday? So these two things together, that's impossible. So since the opposite statement can't be true, that must mean that the original statement has to be true. So now let's apply this logic to our statement, that 1 is equal to 0.9 repeating. So to use the method of contradiction, we're going to assume that the opposite is true. So we're going to assume that 1 is not equal to 0.9 repeating. So this means that 1 minus 0.9 repeating is not equal to 0. So if we're assuming that 1 is greater than 0.9 repeating, then there must be some number in between 1 and 0.9 repeating. Well, this number has to have a ones digit of 0, because if it did have a ones digit of 1, then it would be greater than or equal to 1, and therefore it wouldn't be between 1 and 0.9 repeating. So if it has a ones digit of 0, then it must have another digit to the right of the decimal point that is greater than 9 in order to be greater than 0.9 repeating. But this is impossible. So this is our contradiction. So we can't have a digit that's greater than 9. So since this opposite statement is false, then the original statement must be true. So therefore we can conclude that 1 is equal to 0.9 repeating using this logic. So here were 3 ways to understand that 1 is equal to 0.9 repeating. I hope you enjoyed.